Hello, everyone. Welcome to the webinar on machine learning-based anomaly detection. Today, it's going to be the third session. So it's an 8-session series of webinars. In the first session, we covered data exploration, essentially learning what the data is like, because that's going to help us in figuring out, what anomaly detection algorithm will be appropriate. And in the second session, we discussed about different algorithms for anomaly detection on independent data. By independent, I mean it doesn't have any kind of autoregressive property, or in simple terms, anything that's not a time series. In today's session, it's all about autoregressive data. In other words, time series data. So for time series data, so we'll be covering a bunch of algorithms. But for all of those algorithms, the core idea is that whether a point is anomalous or not, the algorithm will make use of the most recent data to make the decision. So because it's autoregressive, each point is not considered to be independent. It's dependent upon the most recent data. So the most recent data gets used in all these algorithms to detect whether something is anomalous or not. Again, the anomaly detection could be for a point, or it could be for a sequence. As we'll see, depending on the algorithm, it might be able to do point detection or sequence detection, or both, or only one of them. So it depends on the algorithm. So let's just quickly go through the algorithm. So what I'm going to do is I'm going to do an overview of the algorithms, again, without going into a lot of details because time doesn't permit us. And then I'll be going through two different use cases. Each one will be using a different algorithm. I'll be showing some results in Python notebook. So that's going to be what will be covered in today's session. So the first one is based on forecast. So what you do is you use any kind of forecasting algorithm, whether it's ARIMA or seasonal ARIMA, or if you use deep learning, it could be LSTM. You make a prediction. So you take n data points, and then you make a prediction for the n plus 1th data point, and then compare that with the actual value. Bigger the error, more likely the data point is anomalous. So that's the whole idea. Now with this, you can do either point outliers or subsequence outliers. So if it's a point outlier, you're just going to forecast for only one data point ahead for point outliers. And for subsequence outliers, you're going to forecast a whole time horizon. So for example, you might be using 50 data points, and then you might be forecasting the next 5. So in that case, then you have to look at the forecast error for each one of those 5 data points, and based on that, you're going to decide whether that whole subsequence of 5 data points is anomalous or not. So with this algorithm, you can do both point anomaly as well as subsequence anomaly. So most of these algorithms, they're all window-based. So essentially, you use a sliding window, and window size is a critical parameter. Decomposition-based, I think we may have briefly talked about this in one of the earlier sessions. What you do is you take a time series and you decompose. We know that a time series may have up to 3 different components. There's a trend, seasonal cycles, and the residue, which is the random component. So with this algorithm, what you do is you decompose the time series into 3 different components. So one popular algorithm for doing that is called STL. So once you have done that, you have the 3 components, and then you take the residue component, which is random, and then you use any of the anomaly detection algorithms we had in session 2 for univariate anomaly detection. All those algorithms based on statistical models. So that's the second approach. The third one is dissimilarity-based. So what you do is you you have some reference data, and then you have the data for which you are going to detect anomaly, and you have to have a sliding window. And so as you slide the window over your data, you take that sequence and you find the distance between that sequence and all other sequences of same length in your reference data. Then you take minimum of those distances, and your anomaly score will be a function of that. You can just call that your anomaly score. So this algorithm is kind of unique in the sense that you don't have to build a model. So it's a model-free algorithm. You just use some reference data, which is free from anomaly, and then you just compare subsequences. So it's all based on the difference between the subsequence that you're considering and all the subsequences in some reference data. So it's a nearest neighbor kind of algorithm. So this is computationally intensive because you have to compare. If you have n windows, so it's like a O(n) square, complexity. Like I said, it doesn't require any model, so that's the advantage of this algorithm. But it's on the negative side, it's computationally more intensive. Local neighborhood based. So this is also similar. So what you do is, again, this one is also model free. You don't require a model. So you have a sliding window, and then what you do is, as you're sliding the window over your data, you find all the distances between the data point at the center and all the other data points in that window. And then, so it's based on, again, KNN, K nearest neighbor. You can either have a neighborhood distance, and then you find out how many data points you have within that distance, or you define the number of neighbors, let's say 3, and then you take the average distance to those 3 nearest neighbors. So you can do it either way. So your anomaly score will be a function of that. So in one case, it's the number of neighbors within some threshold distance. The other one is given the number of neighbors, the average distance to the the nearest n such neighbors. So this one is also model free, like the earlier one. Markov chain based. So this one is based on probability. So by the way, the local neighborhood based approach, you can only use it for point anomalies, whereas the dissimilarity based, it can only do subsequence anomaly because you're comparing the whole sequence with other sequences. So what you get is anomaly for subsequences, but the neighborhood based approach will give you anomalies based on individual points. So that's one difference. The Markov chain based also, it gives you subsequence anomaly. So again, you have a sliding window, and then what you do is, this one will require building a model, so it's not model free. So what you have to do is, you take some training data, and then you define a so in your training data, you find you have to discretize your training data. So let's say you discretize, and let's say you have 10 different discrete values. Then you have to build a 10 by 10 probability state transition matrix by going through your training data. So that's your model. So, and then you take your test data, and then you have the sliding window. Let's say your window size is 5. So what you want to do is, you want to find the joint probability of those 5 points. Now, since computation of joint probability is very computationally intensive and you require lots of data, it gets simplified by using this first order Markov chain example. So with that assumption, what you can do is, you can express the joint probability in terms of a bunch of products of conditional probability. And those conditional probability values you can get from the state transition matrix that you have built using the training data. So as you're sliding the window using this first order Markov chain assumption, you have an estimate for the joint probability of that sequence. Now lower that probability, higher the outlier score, because less likely it is you're going to see that subsequence. There are some variation of this. Instead of conditional probability, there are some other metrics, but they all effectively boil down to the same thing. Essentially, what you're computing is, given a subsequence, what is the probability of seeing this subsequence in my data? And again, lower the probability, higher the outlier score. N-gram frequency, this one is a little more complicated. Again, in this also you have to build a model, so you need some training data. Like the previous approach, here also you have to discretize the data, and once you have discretized, you have to decide on a size of n-gram. So n-gram, so each discretized, each discrete value is like a symbol. And let's say you choose a n-gram length of 2, okay? So what you do is you take your training data and then you calculate the frequency of this n-grams of size 2. So you have like a frequency table. And then you have let's see, yeah. And then you also, you calculate the similar frequency table with your test data. And then you compute the difference between the two frequency table. I mean, higher the difference, more likely it is that the sequence that you're considering under your window is an outlier. So this requires a model. It requires training data. Spectral residue based. So this one doesn't require a model. So what you have to do is you take your time series, you calculate FFT, which is fast Fourier transform. So you transform it to a frequency domain from the time domain. Then you apply some kind of convolution on your FFT to smooth your FFT. Your convolution will have a smoothing effect on your FFT. Then you subtract the smoothed or average FFT from the real FFT. So the idea behind the subtraction is that anything odd will kind of stick out in that difference. Then you perform an inverse FFT on the difference, and it's called saliency map. As far as I know, this algorithm has been used by Microsoft in some of their internal projects. I read somewhere. So you take the inverse FFT, so you're back to the time domain, except that you're using a difference between two FFTs. Then, so this gives you a time domain data. The way you calculate anomaly score, you take the average of that, and then you find the difference between any data point and the average value, and higher the difference, more likely it is to be an outlier. So it's a little more complex, it involves a lot of steps. You have to go back and forth between the time domain and the frequency domain, and you have to use FFT and inverse FFT and all that. It's called spectral residue method. The segment method is kind of a generic approach. Now, in the next session, we are going to cover multivariate, anomaly detection, where instead of scalar, you'll be dealing with we'll be dealing with a vector quantity. So with this segment-based approach, what you can do is you can take a time series and you can effectively convert that to a multivariate anomaly detection problem. So for example, if you decide on a window size, you can segment your time series into a whole bunch of segments. So each segment is like a vector of size equal to whatever the window size is. So once you have that, then you basically have a tabular data. And once you have the tabular data, you can use, for example, there are many ways to do multivariate anomaly detection. For example, if you take a deep learning approach, you can use autoencoder. So if you use autoencoder, with autoencoder, the way you do anomaly detection is that you train your autoencoder, and then you feed the test data, and then you look at the regeneration error after it goes to the decoder, encoder, and the decoder. And higher the degeneration, higher the regeneration error, more likely it is to be an outlier. So in this case, the whole segment will be marked as an outlier. So this is also a subsequence outlier detection algorithm. So as you can see, most of these algorithms will only do subsequence anomaly detection. There are a few that can do point detection also. For example, the forecast based, you have a choice there for doing point anomaly detection. This local neighborhood can only do point anomaly detection. You can only detect anomaly in a single point. Dissimilarity-based, this is also subsequence only. The decomposition-based, this one is point anomaly only. And the forecast-based, it can be point anomaly or subsequence anomaly, depending upon how you do the forecast, whether you forecast a single data point or a time horizon. So it depends on that. So that's as far as the algorithm goes. Now I'm going to jump into the Python notebook and run some use cases and show some results. So here are all the links to the various resources that's relevant for this session. So the first one is so the first use case will be using the subsequence dissimilarity algorithm for a rotating machinery in a fault diagnostics. So so we'll be using this dissimilarity subsequence dissimilarity based algorithm for that. Then the second use case is we're going to use the Markov chain approach, and the data set we'll be using is for health monitoring data. It's essentially blood sugar, measurement data. So those are the two use cases that we'll be discussing. So both the use cases will be based on Spark Scala implementation that I have in my open source GitHub repo. And these are the links to the Scala implementation, this one and this one. Now, let's jump off to the use cases, and let's look at some data. So this is the first use case. So typically, in a rotating machinery, if we look at the frequency spectrum, when it's functioning normally, there will be a typical frequency spectrum. When there is a fault, for example, the fault could be, if it's a rotating machinery, it could be some bearing, malfunctioning or something. Typically, that will manifest itself in the frequency domain with some very high frequency components. So your frequency spectrum will change. So, you could take that approach. You can use FFT to detect anomalies, but we won't be going that route. What we'll be doing is we'll be taking a subsequence, and then we'll be comparing that subsequence with all the subsequences of same length from some reference data. And then based on the difference, we'll detect whether a subsequence in the test data is anomalous or not. So we'll review and explore the data set. Algorithm, we already went through it, how the algorithm works. I'll spend a few minutes with the Spark Scala implementation. Again, I don't have time to get into a lot of details. We'll look at the configuration. Like I said last time, all my Spark jobs, they are heavily configuration driven. I use a JSON-like syntax for configuration. I'll be showing you some samples, and I'll run the Spark job and review the output. So here's some data. So this is normal data. This doesn't have any outlier. I'm just showing a small section of the data. It's not the whole data set. This is autocorrelation, just to show how autoregressive this data is. And as you can see, there are all kinds of very large peaks in the autocorrelation. That means it's highly autoregressive because you have very large peaks in the autocorrelation. Next, we are going to look at some data. So let me actually run this also quickly. Let's see. So I'll start my Spark. It's a single node pseudo cluster that runs on my laptop. And I'll be using a shell script to run this Spark job, and this is the shell script. So it runs this particular Scala class, Subsequence distance detector. I can quickly show you. This is the Spark Scala implementation. As you can see here, window length is an important parameter. That's window size. And this is the configuration file. See, I've set the window size to 40. You have to also set a score threshold. It's set to 0.2. We'll talk about that more a little bit later. And this is a reference file that the sequence will be compared with. So that's the path to that. And these are various kind of metadata configuration. It tells you, which column is what, all these things. So this one tells you the first column is the ID for the data, which is ID for the machine, particular machine. So this data set has vibration acceleration data for 2 different machines. This tells you that the third column is actual data, acceleration data, and this tells you that the second column is a timestamp in milliseconds. So now I'm going to run it. So it's running the Spark job. This data was created with a Python script. So it's just a combination of a bunch of sine waves with some random phase applied to each one of them. Oh, something went wrong. It was running yesterday. I may have done something. Sorry about this. Yeah, I don't have time to troubleshoot this right now. It was running yesterday or day before yesterday. I don't know what changed. It's a weird error message. Doesn't make any sense. 142. Let's see. I doubt I'll have time to fix this. I just have to move on. Anyway, let's just move on. So, so this is the last time when it ran successfully. I created this Python notebook. So the first chart shows us the outlier score. And I'm showing the outlier score around where, so the way I introduce outlier in this data set is that I took some test data, and about halfway through, I inserted some high frequency, sine waves into the data set, which is supposed to simulate, some sort of fault. So, and I'm showing the outlier score around that point where the high frequency components were introduced into the time series. See, the outlier score, goes up. And this is the complete data set, and the red lines are the outlying points, the outliers, actually. And as you can see, halfway through the data set, the outliers start showing up. So one of the issues in any anomaly detection is how do you set that threshold? So you have an outlier score, and these are the outlier score values. And in this case, I just chose 0.2, but how do you know that, what's the, I just picked that value, but there's no real justification for that. So one way to do that is to take all these outlier scores and do a statistical test. And that's what I did here. So I took the outlier score, and there's a Python script which takes the outlier scores and gives me the upper tail statistics of the outlier scores. See, the 0.2 that I had, that roughly corresponds to this 0.9, which means an alpha value of around 0.1. So that means about roughly 10% of the data is outlier according to the threshold that I had chosen. And I can show you that. Sorry. See, the threshold I had chosen was 0.2. Now, if you go back to that, so instead of an alpha value of 0.1, you might choose 0.05. In that case, you'll be here. So you should set your threshold to 0.469. So it's kind of tricky how you choose the right threshold value, and it's kind of subjective. So I think the best thing you can do is this kind of statistical test, where your null hypothesis is that the outlier score doesn't correspond to an actual anomaly. That's your null hypothesis. So if your null hypothesis is rejected, then it's an anomalous data point. So that's what I was doing here. So based on this, you might decide to have an alpha value of 0.05 and have this as a threshold. So in that case, you can go back to the configuration and change this threshold, and then rerun the Spark job. So the second use case is based on it uses Markov chain. So this one actually involves, it's a little more complicated. It involves multiple Spark jobs, because first we have to build a model. Now this one didn't require a model, so it was simpler. So this one you have to build a model. Now to build a model, you take some training data, then you have to discretize the training data. Then you have to build that probability state transition matrix. And then finally, that's your model. And finally, you run the anomaly detection Spark job. So if you look at the, so there is a shell script for that also. If you look at it, you'll find multiple Spark jobs. This one uses a Spark job called data transformer. It's actually a ETL kind of Spark job that can do all kinds of data transformation. And in this case, it's just going to do discretization of the data. So you specify the width of the I'm sorry. You specify the step size, and it'll discretize your data. So here, the step size is set at 5. And then, so that's the first Spark job. And the next one will take the output of the first job, and it'll build that probability state transition matrix. And then the third one will take the output of the second one, which is the model, and then run the actual anomaly detection Spark job using that model. And that's actually here, Markov chain predictor. And for that, so here's some data. So as you can see, the data kind of stays around 100 or so, and then there are some spikes, occasional spikes. So here the whole idea is that so this measurement is done once a day. So there are lots of people, and they have their own device, and they measure once a day, and the data gets uploaded somewhere, and then it gets analyzed to see if there is any anomaly and any kind of serious health condition. So here we are interested in doing subsequence anomaly detection, because if it just spikes for a day and then comes down to normal, we are not so much concerned about that. But if it spikes and then stays there for some consecutive days, then that's what is concerning, and that's what we want to detect. So that's why we need an algorithm that can do subsequence anomaly detection. Here is the autocorrelation for the data. You can see some autoregression. There are some spikes in non-zero phase lags. Here is some sample. Here is some outlier score. See the outlier score kind of going up and then out down again. And this shows the red lines indicate outliers. See how the measurement goes up and then stays there for like few days, and then so that whole sequence is marked as an outlier. So again, that same threshold issue also comes up here. So if you go back to, if you look at the configuration for this, let's see. Yeah. So this is a configuration file for this use case. As you can see, since there are 3 Spark jobs involved, there is one configuration block for each Spark job. This one is for the data transformer, which does the discretization of the data. Then the second one is for the state transition probability matrix. And the last one is for the actual prediction. So here also there is a threshold. So in this case also you can do something similar like in the other case. You can do some statistical tests to find out what should be the appropriate one. This one is kind of just selected randomly. Something, that that's reasonable, but really doesn't have any kind of statistical foundation, behind choosing it. So for this also, you can do something like what we did in the first use case. You can take all the outlier scores and get the tail statistics, and then using that, you can choose the appropriate, threshold corresponding to whatever alpha value you want to use, 0.05 or whatever. I haven't done that, but that can easily be done. So there is a Python script for doing that. If you because the way in the output of the any anomaly detection algorithm is the output format is essentially the input record followed by 2 extra fields. The first one is the anomaly score, and the next one is the anomaly level. So let me show you some. Oops. So here, see, if you look at any record, except for the last 2 fields, it's essentially the input, which is some device ID followed by timestamp followed by some measurement, blood sugar. So, and then this one is the outlier score, and the last field is the label for the outlier, where the N means normal, O means it's an outlier. So this is O. Now this value you see 17. So this is the discretized value, and the step size was 5. So actual value is 85, not 85, 17 times, yeah, 85. You see some really high values here, 35. Anyway, so when we calculated those stats, it took the output and it picked up all these outlier scores, and that's how it got the tail statistics. Now, yeah, so that's what we did. Let's see. Okay, I think I'm going to stop here and see if there is any question. Let me see if I have shown you everything from here. Yeah. Oh, let me show a few other things. Some implementation of the Markov model predictor. Yeah, I think I already showed that. The Markov model. Oh, this is a predictor. Yeah, I think I've already shown that. You can see there The second use case involved a few other, two other Spark jobs. Let me see if I can show those quickly. The data transformer, I'm going to skip that. And Markov chain predictor, yeah. So this is the one that builds that state transition matrix, Markov chain predictor. So that was no, sorry. Data transformer. State transition model, okay. This is the one that builds that the model, Markov state transition model. Okay, so that's in a different. Let me see if I can find that quickly. That's in a different repo. Yeah, that's this. So this Spark job, it creates that state transition matrix, which is the model. So this is the second Spark job in that workflow. It takes the discretized data and creates a state transition matrix, state transition probability matrix. So I'm going to stop here and then see if there are any questions. Hello? Sharon, are you there? Hello? Hello? Sharon?
Yes, Pranam, yes. Waiting for a few more minutes for any questions there.
Okay.
Yeah. Okay, if not, you can also leave your questions at info@elephantscale.com. Otherwise, we will be sending the recording in 2 days' time. And also, we'll catch up for the next session on November 20th, the Friday.
The next session will be 20th, correct? Yes.
Yes, 20th, yes.
Correct.
Yes.
Okay.
And the next session will be on multivariate data anomaly detection on Python. So that will be session number 4.
Okay.
So yeah.
So should we
call it off now? Yeah.
Yep.
Yeah.
Okay.
Yeah. We'll wrap. Thank you so much, everyone, and thank you, Pranav. Thank you for the great session.
Yeah.
Thank you
Thank
so
you,
much.
everyone. Bye-bye.